Welcome to our channel for probability and statistics. In this video, we will talk about central limit theorem. The central limit theorem is talking about with the sampling distribution, and more specifically, it's for sampling distribution of the means. So, for example, if we want to estimate the population mean, and we take several observations from a normal distribution with mean mu and variance sigma square. So the important thing of this distribution is that the sampling distribution of the x bar, which is the average of xi, I from 1, 2, 3, 4 to n and so on. So by reproductive property of the normal distribution, we can conclude that x bar, which is the mean of sample summation, has a normal distribution with mean equals n1 divided by n times n mu, which also equals mu, and the variance called sigma x bar square, which means the sampling distribution's x bar's variance. And this variance equals the population variance divided by n. So sampling distribution of x bar means the sample average has a normal distribution with the population mean mu and the population variance divided by n of its own variance. And if we are sampling from population with unknown distribution, so from the previous page, we know that population is normally distributed. But now if the population distribution is unknown, either it can be finite or infinite, or discrete or continuous, and so on. But the sampling distribution of the x bar will still be approximately normal with population distributions mu, average, and variance sigma square divided by n. This is same as before, but provided that the sample size is enoughly large. So this amazing result is an immediate consequence of the following theorem called central limit theorem. The central limit theorem states that sample average x bar is the mean of a random sample of size n taken from a population with mean mu and finite variance sigma square. Then the limiting form of the distribution of this statistic called Z, which equals sample average minus the population mean divided by population variance divided by the square root of sample size. This statistic Z, when the sample size approaching infinitely large, is the standard normal distribution variable Z with mean 0 and standard deviation 1. So this is the central limit theorem. And the central limit theorem has prerequisite that a sample size, if larger than 30, this means enoughly large, and the population distribution is not terribly skewed, so the approximation is very good. If the population is not very different from a normal distribution, and if the population is known to be normal, so the sampling distribution of x bar will follow a normal distribution exactly, no matter how small the sample size. So if the population is known to be normal, so the sample size is not so strictly important, because the sample average will vary closely to the normal distribution if the population is normal. But if the population is not normal, you have to be with the sample size at least larger than 30, and the population is not very skewed because the normal distribution is symmetric. So in this case, the approximation is still good to be approximately normal for the sampling distribution of the average. So from this figure, list several sampling distributions density curve. For example, if sample size only 1, though this curve is clearly not normal, right? But if the sampling distribution with the n very large, so no matter what kind of the distribution for the population, its sampling distribution will still very close to normal. And for small to moderate n, it look like approach to normal, but still has some skewed to the right, right? So we look at an example now using central limit theorem. An electrical firm manufactures light bulbs that have a length of life that is approximately normally distributed. So here the population is normally distributed with mean equal to 800 hours and a standard deviation 40 hours. So both the mean and standard deviation of the population known. And the question is to find the probability that a random sample of 16 bulbs will have an average life of less than 775 hours. So the solution is, because here the population is normal and the sample size is moderately with 16, not over 30, but not very low, with only 2, 1, 2, 3 samples. So this is moderate sample size. So the sampling distribution x bar will be approximately normal. So with the mean of the x bar will equal the population. This means the central around the population mean, right? So central limit theorem, which means the sampling distribution of the sample average, because if we get many times of different x bar, it will also has a distribution, because not all the x bar will be the same, right? So this x bar will center around the population mean. So here we say the mu x bar will be 800, and sigma x bar will be the population standard deviation divided by the square root of 16. Because if we take a square, so which means the sigma square of x bar will be the population variance divided by sample size. So here we take a square root with the standard deviation divided by square root of the sample size, so which equals 10. So sigma standard deviation of the x bar will be 10. So the desired probability is given by the area of the shaded region in the following figure. So we look at this figure. If you want to know the probability of less than 775, here is 800 sampling distribution of the x bar. Sampling distribution of the x bar will be at the center of 800, right? Approximately normal and with a standard deviation of 10. So if you want to know the probability of this sampling average lower than 775, we just want to calculate the probability of this shaded area, right, for probability. So we find for the standard normal distribution, this value minus the mean divided by the standard deviation will be a Z value will be a standard normal distribution random variable, so which equals minus 2.5. So from the standard normal distribution probability table for this critical value, this random value or quantile value, can find the probability of x bar less than 775 equals probability of Z less than minus 2.5, which is 0.0062. So this probability is quite low, very low. It's less than 0.001. So less than 1 of 1,000, right? The probability also less than 1 of 1,000. Thanks for watching.